Welcome everyone and thank you for joining this presentation. My name is Kerman Viana. I'm a PhD student at the Basque Country University, and before that I worked as a research member in the Computational Intelligence group from the same university. As we can see from the title, this presentation will focus on neural network modeling of a twin rotor system, which involves many difficulties compared to other dynamical systems. To understand those difficulties and address the developed modeling solution, this presentation will be organized as follows. First, the motivation or need of a twin rotor system modeling will be explained. After that, we will briefly describe the particularities of the twin rotor dynamical system. Then we will focus on explaining this study's framework, and next we will describe the neural network modeling system optimization steps followed during this work. And finally, the obtained results will be presented and analyzed, which will lead to the final conclusions. So first, we will start by explaining the need or motivation for this work, which, as we said, involves the modeling of a twin rotor system using neural networks. This need comes from the development of a predictive control strategy designed by the Computational Intelligence group within the Basque Country University. This strategy aims to obtain the control signals for the desired behavior of a dynamical system based on genetic algorithm. With that goal in mind, this strategy requires of a model for the control system which should be not only precise but also lightweighted in terms of computational cost. We can confirm that system modeling has been previously addressed by the use of neural networks with good results, both for linear multiple variable systems and also nonlinear single variable systems in the framework of this strategy. Therefore, the present work will base its studies on those results and move forward to model a nonlinear multiple variable system. This is the twin rotor, both in a simulation benchmark and also making use of the data from the real platform. But before we talk about the modeling itself, we would like to highlight some of the particular features of the twin rotor system. First, in case anyone is not familiar with the twin rotor system, we just want to point out that it's a mechanical model consisting of two rotors placed on a beam together with a counterbalance. Therefore, there are two variables involving the movement of the platform: the pitch angle or elevation angle and the yaw angle or azimuth angle. This way, if both variables are taken into account, the twin rotor system becomes a MIMO system. Besides that, the twin rotor system also exposes clear nonlinearities mainly because of two different sources. First, the equations for the 2 degrees of freedom clearly show that both pitch and yaw angles affect the other degree of freedom in the so-named couple effects. And on the other hand, interactions between the electrical and mechanical systems for the twin rotor platform also derive in some external nonlinearities that, of course, can only be seen in the real platform, where they can't be ignored. So, as we said before, the goal of this work was to obtain a model of a nonlinear MIMO system. Therefore, we should focus our study into regions where these effects can be exposed in a clear and meaningful way. As we can see from the picture in the slide, and according to mathematical equations, nonlinearities exist in both degrees of freedom, but they are much more meaningful in the pitch angle range of action. Also, we must underline that those nonlinearities have been proved to be close to the boundaries of the twin rotor both mechanical and electrical units, and thus they are not commonly noticed in regular movement behaviors. Therefore, and in contrast with the rest of works regarding the modeling of the twin rotor platform, this study will focus on modeling not only the commonly studied and more linear regions, but also those boundary regions where nonlinearities are clear. Besides that, there are two other issues that must be addressed and matched with the region of interest requirements. First, an appropriate sample time must be established for the modeling system, so it matches the amount of predicted steps that the model is able to predict according to the system dynamics. This sample time election must also be valid for both simulation and real platform study stages. On the other hand, reference profiles for the model training and validation stages must be chosen in order to assure that main dynamics and operation points are all considered. This was made possible using smooth transitions between differing operation points. So, in this next chapter, we will explain our modeling methodology, adding some numbers and details to the optimization process. And just before that, we want to highlight that this methodology was implemented both in the simulation and the real platform stages. With the data acquisition. For the training stage, we use an exhaustive dataset covering all possible operation points for the twin rotor system. On the other hand, for the validation stage, we just want to avoid the well-known overfitting problem, so we will use a less exhaustive dataset. Regarding the neural network for modeling, we choose to compare single NARCS MIMO networks with 2 inputs and 2 outputs according to the 2 degrees of freedom. But to obtain the optimal structure, we vary the structures changing the number of hidden layer neurons and input and output delay values. Next, we choose a prediction horizon both for the training and validation stages according to the fixed sample time, which was set to 0.1 seconds. Therefore, prediction horizons of 40 time steps, which correspond to 4 seconds, were accepted as enough to satisfy the control strategy requirements. Finally, and with the goal of avoiding statistical dependency, we performed 5 batches of successive training and validations with the same neural network structures. So, with all that in mind, in the next slides we will show some of the results we obtained after the already mentioned process. In the table from the slide we have now on screen, we can see the top 10 network structures that have obtained the best performance during the validation stage, measured by their mean square error throughout 5 iterations. The first and most obvious conclusion will be that all 10 structures offer a very successful performance when predicting the twin rotor dynamics quick enough so the control strategy can work properly. But besides that, and from the small difference between the top performing network results, it's not clear to say that the top performing network from this table is definitely the optimized structure for this problem, but rather that all structures obtained from the organ optimization process and exposed in the table may fulfill the requirements of control strategy, and therefore that all are valid for our purpose. Anyway, in this next slide, we want to show the top-ranked network structure in action, both for a simulation and a real platform stages validation dataset sections. In any case, I believe that it's quite clear that the best network obtained from our optimization process fulfills our work's goal of modeling the twin rotor dynamics time ahead for the predictive control strategy. So finally, to sum up with the main ideas of this presentation, we want to highlight the contribution of this work and the main conclusion we derived from the previous analysis. With the contributions, in this work we have studied the regions of dynamical action for the twin rotor, where nonlinearities appear in a more clear way and are easy to identify, regions that the rest of authors usually avoid because of the difficulties they bring to the modeling process. We have also proposed a methodology to model the full dynamical range of action for the twin rotor model based on MIMO neural networks and using datasets obtained both from a simulation benchmark and also the real platform itself. And as conclusions, we would like to underline once again that the obtained models are perfectly viable for the purpose they were made for and offer very little deviation from the real dynamics. So thank you very much for joining this presentation, and I hope you all enjoyed it.